Okay, hello everyone. Today, Aziz Kharoof is going to tell us about simplicial methods in the resource theory of contextuality. I think this is a follow-up to the talk sequence from last term. It's kind of the final talk on bundles and categories constructed from there. Okay, Aziz, please go ahead.
Thank you, Cihan. Thank you. Okay, I start to remind you what we are doing. So actually, in the simplicial distribution approach to contextuality, we have a scenario. So the scenario is consists of measurement space and outcome space. So usually the outcome space will be delta of Zm, with saying that for every measurement there is m outcomes. Okay, and the simplicial distribution, like this is simplicial sets and this is simplicial sets. Maybe I can remind you what is this simplicial set. This is the following simplicial set, that in the 0 degree it's this, the 1 degree it's this, like this, yeah. Where the faces maps are only deleting and the degeneracy is by cupping, yeah. Okay, anyway, but this space actually telling me that here we have m outcome for every measurement space. Ah. The simplicial structure is not clear, maybe. Okay, simplicial sets, you know simplicial sets. So we are the simplicial distribution. What is simplicial distribution? It's a map. It's a map from here to the distribution of. Okay. So what it's give us, like let's say that x is this, for example. So just simply something simple. This is x. Yeah. So what is this give you? Like map like this is defined, of course, by this, like this. Let's say this is sigma 1. This is sigma 2. So it's defined by two, like by what is image of p on sigma, like p sigma, which is will be, because it's one dimension, it will be some distribution on here. Okay, and p sigma 2, it will be the same also, some distribution on here, but because of they share a point here, okay, they share a point, okay, so they will have the same, like when we, because this is simplicial map, yeah, this is a simplicial map. So when you marginalize to, like you going to this point, the distribution of this point, so there is a map that by deleting one of them going to this one is the same, so they will be the same, yeah. So as you can, okay, think about something more complicated, so it will, so it's some distributions that glue together. Okay, so this tell me like what is the distribution to be here, like we think about this as every one of this is measurement and this is context, like we can do this two measurement together, like, and this also we can, and we have the results, so distributions of the results, so it's like this. Okay, so this is and the simplicial distribution, like it's the distribution that we get. Okay, like okay, for this, so this is explaining the scenario, like this is, so this is called the measurement space because it's including the measurement and what I can do together. So this is called the measurement space, measurement space, and this is the outcome space. Okay, space, yeah. But actually in this language, of course you can change here to any simplicial sets, but usually this is what we choose because, okay, this is telling us like every measurement has m outcomes. Okay, m outcomes. But this is the thing, like we need now to generalize this language in order to, because sometimes like this measurement have two outcomes, but this measurement have three, and this measurement maybe have 10 outcomes. Okay, so this is maybe one of the things that we need to generalize like this in order to get this. Also, in terms of morphism between scenarios, because okay, this is one scenario. let's say, and this is other scenario y delta zk. So we want some morphism between scenario. How we can get morphism between scenarios that induces a morphism between the simplicial distribution, because all the simplicial distribution, if we take all the simplicial distribution on this, like the set of simplicial distribution, it will be convex set. Okay, it's convex set. So simplicial distribution of x delta z m, we mean all the simplicial distribution like this. Okay, so it's give me a map from here to here if we have a map like this. So one can imagine it's easily, because actually, like in fact, what is this? In fact, this is exactly all the simplicial sets definition from x to d delta zm. Like this is simplicial set, this is simplicial set, but also when we apply d, when we apply the distribution, why, you understand what I mean by d, the distribution monad? Sorry, I didn't maybe say, yeah, distribution monad, when we apply on this, so it's this will be also simplicial set. So we have this, and we have here this. So of course, if what is the map for that induce a map from here to here? What is the map? It's two maps, like map from y to x, right? Because it's contra, like, and map from this to this. So pair of maps, like from from y to x, and a map from this to this. Okay, these two maps. But we see like it's separated. The map is separated. This is also one of the things that we want to derive, because sometimes like we're interested of the maps that like not thinking only about the maps between the measurement spaces and maps separated. No, we want something mixed together. Okay, so this is the thing. So we want to mix the outcomes and the measurement space, not like this separated, because one of the things here that we have for all of them, we decide a unique number of the outcome which we want, and also for here for the morphism between them that induce morphism between the simplicial distribution, it's will be also separated. So the idea actually to put the measurement space like this here, and to put above this all the outcomes. So, and here we will have another space called its E that have the outcome. So how I can explain? Like for example, in our example here, like this, for example, let's say here m outcome for them. So we can do this because we can put, okay, this is x, and here how we can build E? We can build E like this. Like I want m outcome for this. Let's say m is 3. I'm here for this, and here all the z3 cross z3, all of them will be here. And for this is the same. Yeah. So this will be our scenario. So our scenario is a map where the measurement space is the base. What? What? I don't understand what you mean by growth. Growth and reconstruction. I will use growth and reconstruction. How you feel it from now? I don't know. Like what you. This is growth and reconstruction. You think? I mean, I don't know. Maybe you think that moving from here to here, I took the category of element, maybe, and I maybe no, not now. No, yeah, but it's related somehow. Yeah, it's related. That you feel it. Yeah, it's related, by the way, but it's hard to explain. What the? Yeah. We can do this, but no. Maybe he feel something else. Like if, by the way, but if we are working over the boolean and do the category of element, we will get this. Like maybe like by the taking the category of element. Yeah, we will use this later, but And now, but the thing that here we can, okay, we can build something like this when this measurement have like here 5 outcomes, and this one have 3, and this one have 4, for example, right? We can do this. Even we can choose here, like it's so flexible, this language, because we can choose that not everything, like, okay, this, for example, this measurement have 4 outcome, and this measurement have 3, but for example, they can't get together, like, I don't know, 0, 1, 2, 3, like this, they can't get together, 3, 3, both of them, or 3, 2, they can't get together, so we only allow here this, like this to all of them, but this not, yeah, we miss this one, for example. We can choose whatever we want, like this is more for people from physics, this is more flexible, right? They can describe more things when we put this above. So in the first problem that we, in this language, we choose only the same number of outcome for all of them. It's solved. Even we have more flexibility here. The other thing about the morphisms between two scenarios. Now our simplicial scenario, it's not like this now anymore. It's not like this. Our simplicial scenario is this, which is called simplicial bundle scenario. So simplicial bundle scenario is only a simplicial map like this, okay? And of course, this is the measurement space. This is the event space, because it's it's not the only the measurement, because it's tell me like also it includes the information about the every measurement and the outcomes, or every context and the outcomes that we can do, all in this one map. And this, of course, included that language. Also, what Cihan said, like we can, because we can choose this to be x delta zm, or as I explained here, also we can do this. Of course, like one can say that, okay, but you need maybe some properties of this, like one obvious property that should be surjective. Otherwise, okay, why you put this measurement if there is no outcome above? Yeah. Anyway, okay, let's say this is surjective, it's enough for our theory. And the other thing now, we want how we can define a morphism from two scenarios like this, okay? This is simplicial bundle scenario. This is another simplicial bundle scenario. So the idea that we can do like from y to x, as we had before, like a map between the outcome. But now, okay, it's not like from this to, now we want to g, right? To arrive to this is a g. Yeah. It's not a map, but it's a map from the pullback of this, with including the information, like the pullback will give me new scenario if I take the pullback. So then we will get here a new scenario. Let's call this f pi. This is a new scenario. Yeah. And now it's to, like, again, like before, like a map between measurements and the map between the outcome. But no, it's included the information, because this map depends on pi. We see this, right? Because the domain of this is the pullback of this, right? So it depends of pi, okay? Like we have, like what it's mean, like we have something here, y, and this alpha actually, it's going to something here, x, but okay, but this alpha from the pullback, like I need something here, like e, let's say, that going to the same place. So I applying this on EY. So it's depend what it's pi here, right? Not only depend on F and G. Okay, so this is not separated here in this. This I will show you later, maybe in when we apply, because we want now to get from this a map from simplicial distribution on this, on F, to simplicial distribution on G, right? We want it to induce a map from here to here. It's much complicated than before, so it's even I didn't define yet what is simplicial distribution on such a scenario. So let's me define this, and then how we can get this map, we will explain in much general language. So we say that, okay, we have here the X, the measurement space, and above the event space. So how we can define simplicial distribution on this? So simplicial distribution, in fact, like it's for every X here, we have a distribution on the preimage of this, right? Because in the preimage, as I explained before, like we have something here like this simplex. So the preimage of this including all the outcome of this that can be, right? All the outcome. So it's something in the preimage of X, right? Like for every X, so it's like this, like we have many for every X in X, I mean like in any degree. We have some distribution in the preimage of this, but of course they are compatible. Like if we taking the like if we taking now p d0 of x, so it will be in -1 of d0 of x. So this should be coming from this, like this inducing by this. Okay. How we can do this in easier? Like we can say that a simplicial distribution, as before, it's a simplicial map from here to d of this, that making the following diagram commute. Like here we apply d on this, on the scenario, and here we take the unit of this. Yeah, send everything to the distribution of 0 and 1, like this, send like x in xn to dxn, send this to delta distribution, like that they have for only for x1 and the rest 0. So if one can think like really this, that the diagram here commute, it's mean exactly that they are, first of all, they are compatible because this is simplicial map, but also this saying that px is exactly in here. Yeah. That's it, you know, that. Yeah, that's a set. Yeah, yeah. But of course, like it should, what you say, maybe because we are using ZM and C group, like, and if we're using something here, so there is a group structure. Yeah, right. There is a monoidal structure there, right? Yeah, there is some monoidal structure above, but it's not really useful for our this talk. Yeah, but if you choose, like, it depends what you choose E. Like you should choose E to be simplicial monoid, let's say, or simplicial group. Yeah, like if we taking, it's not really, by the way, like this, maybe no, not like, yeah, I remember we have this in this theory, in the theory, but in this you can do, it's not exactly like, if you do like this, for example, the product, it's not exactly that this is a simplicial group, right? Because it's a product of X, but like for every this is simplicial group. Like there is like a grade is some in some compatible way, some simplicial group. Yeah, there is some structure there. Yeah, yeah, right. F to be a principal K bundle when it's simplicial group K. You maybe did this in your with the twisted. Yeah, yeah. I'm not. I wasn't part of this. Yeah. So we can take, so the other no, no, it is, we want to get something new, yeah, in comparison to the product case. So if you take a principal bundle which doesn't split, then you can get something we call twisted distribution. So that's kind of the case I think you're asking for. Okay. So what I want to say, okay, so maybe you understand what is simplicial distribution, but it's really like, it's now hard really to show that this map, okay, it can be shown, but we will show it in more general way. So let me move to define something more general that can help us. So our goal, before maybe started with this, what is our goal? Like to define this as a category. Like there is morphism. We say like, okay, we have some category. We called it the simplicial scenario. what is this category? The object of this category, we want it to be like only simplicial bundle scenario, and the morphism as there, like as we explained there. But of course, we need to explain the composition, and also we need to explain. We want also what scenario, like simplicial scenario, yeah. So, but we want this functor, this to be functor, the simplicial distribution, this functor to be like going from this category to convex set, okay? To be a functor, like not only we already, what is the object in there? Like, okay, for scenario, there is this. So also we know how it looks, the morphism, but we want also to explain the composition and explain that really this is a functor. So in order to do this, we'll explain something more general construction, which is a scenario over monad. So let me explain this. Let's start from this, like when we have a category and we have a monad on this category, like monad. So let's say we fix some x in C, object in C. We define the following category, the category of bundle Tx. This is the category where the objects are morphism in C. Okay, the objects are morphism in C, and the morphism from one object to other, it's something like this. Let's say call it alpha, and this is dg. So this is a morphism from F to G. Okay, this is a morphism from F to G. This is a G from F to X. Okay, because all of them bundle with the same X, like X is fixed from the beginning. Okay. So what is this category for anyone? Okay, at the end of the day, we will use here C to be the simplicial set and T to be the distribution monad. Okay, but we now doing some general construction. So this category actually generalizes two things in the same way. What? T? No, TF. Like I want, okay, maybe I didn't explain. Like here I want a morphism from, this is morphism from this F to another object in the same category. So another object X, it's fixed. X is fixed. Yeah, maybe it's remind you there, but it's something more like it's remind you what this. We will explain why it's how it's related, but this is a morphism from here to here. This is so what it's remind. It's remind Kleisli, right? Kleisli category. Like so, if we taking actually, if X is a point like terminal object. Let's say that C, we will ask later that C to be with all the finite limit, okay? Like let's say this is with finite limit. But if, why I'm saying this? Because if X is the terminal object, then it's a Kleisli morphism, right? And here also the composition, it's a Kleisli, like how we compose, like a Kleisli, like if I have now another one, like from F to I don't know, G, like H. And here we have another morphism beta. Yeah. So we're doing this using class, like what we are doing, like as a composition in class category, like we apply on this T, right? T beta, Tg. Here was Th, so it's twice Th. Yeah, and T on this, T on this. So this is the same, like same. And then, of course, we apply mu. And here Tx mu. So this actually, in fact, one can see that, okay, this is the Kleisli composition, so this is the map, but this is the same type of maps, right? Because here, this composition will be, this is the identity. So this composition will be delta x, right? So the composition is work, and really, if we're taking x to be the terminal object, then what we have actually here, like nothing, like we have, and we should ask that T is what it's called, like when maybe you remember, Cihan, when it has this property T, it's called some affine maybe, yeah, right? Yeah, when it's sent terminal object to terminal object. Okay, we can ask some property for T. So this, okay, let me write it's in green. If we ask also this, so really it's generalized. Like if this is x equal to this, then this is a Kleisli, like where it's then bundle like T of this is exactly like the Kleisli, how we can, like this is T. Okay, and it's generalized another thing, like if T is the identity monad from C to C, identity monad, then what is this? This is a slice category, right? Then bundle like the identity monad over any x, like it's exactly this slice category. Okay, so this generalizes this both this definition. So okay, let me move there. And in fact, like see here, like act on this on category like by this. Like I can explain, like we have here, like we have an object on C, like this X, and we built the category right here. So one expect maybe if we have morphism here, yeah, to have here a morphism between a category. So if we have this morphism, actually it's contravariant. Okay, so if we have this morphism from Y, so it will give us a functor from here to here. Okay, it will give us a functor. So let me maybe explain this and what we need for this. So I will add there in green what we need for, because I already only added that, okay, this is with finite limit and this property, but we need another property in order to do this, in order to get like here a functor, like every object give me a category, every this give me. So why I'm doing this? Because exactly I want to get like a functor from this bundle T to be a functor to categories, and then I can apply Grothendieck construction. Yeah, in order. Yeah. Exactly. Like let's do this exactly. So, but we need something. Like let's do this, and then we can think about what happened. So we have what we want. Like we want something from here to here. So we want every bundle exactly this in terms of as you say, like this to get, and we have a map. So we're taking the pullback exactly. So we can take a pullback of this. This in terms of object. So let's call it f pi. So actually, in terms of object, this one sending f to this f pi. But now in terms of where we are going to. Yeah. So in terms of maps, so if we have a map, like let's say here we have a map from what I want. Yeah, exactly. I want this delta x, right? Tx. This is a map, right? From here to like alpha, as we explained there, to tf, let's say here tj. So what we can do in order to get this, so one can do also the same, the pullback. It's not good picture because I didn't maybe wrote it in the good, but one can doing here like to taking here the same like t of pi, here t of y, and here to take this delta of y. You can, it's not good, right? The picture, it's not, I can maybe write it again to be like better. No, not to be better. I think if I'm writing like this, y, e, this is f, and we taking here the pullback. This is f pi, right? And I want here to have this, there is y, this y, sorry, there is tx here, and we have above te. So there is this is a map. Let's say this is a map. So we want to do a pullback for a map, right? Like this is alpha, this is delta x. So let's do this, and we have here by taking, like we can take here to be t y to be also again delta y, and here this one to be this is from here to here, sorry, this is pi, so this is t pi. Yeah, and we can taking this map, then we have a map from the pullback of this to the pullback of this. To the pullback of this. So this is map. How we can call this map? So this map we can call it alpha delta y, right? Alpha delta y, like it's morphism of map. But the thing that this map, it's not and here it's not really a map from the morphism, like because we need here a map from f pi. This band, it's not like this is functor, like normal functor. So we need from f pi to f to g pi, right? But here it's not like here appearing f pi. So this commutative, it's okay, like here f pi, but here it's not g pi, right? Yeah, you see, not g pi. So in order to do this, we need to use the gluing here. There is if we have 40, of course, this is exactly the conditions that I wanted to ask, but we have for all of this, we have for the distribution monad. So we have a map like from this pullback, we can glue like and have a map from, like always when we have pullback, we called it M. Okay, so of course it's M depend on the maps, what we have in maps, but we call always M. The thing here that this M, it's here if we take tg, t just a minute, t y, and here tg, so this actually commute. We can prove that this is commute, and really we can take this, so then this will be, you see, like this is our map. So our maps here, it's M alpha. What? Actually, there is for product, people using for when they using like monoidal monodes, then monoidal monad, then they need for a product, right? They need for the monoidal, like they need okay, they have, okay, let's say even it's a product, you have a product like a Cartesian monoidal, then you have this map. Actually, they ask, okay, you have this natural map with some properties, right? In order to move and to make like the Kleisli category is also monoidal and things like this. But now this must generalize exist because it's for pullback. So people, yeah, it's something, but it's not have all the properties, a good property for that. So I will explain what this property, what we have in a property. Yeah, exactly. Actually, in fact, like people, what I'm searching, I search about this, Cihan, like we found that like people use this, by the way, this gluing like for pullback, especially for distribution monad, but it's not all the property known. Like some people know this property because they used here, but now we'll the property we need in order to construct this. Because what we need here, now, okay, for at least for defining this, we need this map. We needed this map. But I think here also we needed, because of this, we need also to say that this map is a section of this, or the natural map from here to here, because there is natural map to the pullback to this. So this is a section for this. We need this in order only to define this. But in order to prove that really this is a functor, we need some property. And in order also to prove that this is a functor, because we need to prove that this is a functor, like this is a functor, okay, so everything going to a functor, but also this functorial, in functorial way. So in order to prove all of this, I'm not going to do this, we need this properties. So I can write for you the properties that we have for this T, for this gluing, what we need. Where I can write it's, yeah, yes, distribution monad, that's fine. The identity monad, no, it's so simple. Another distribution, like, okay, like there is like, but it's the same like as distribution. This when you take the subsets, this one of so, but it's like Boolean, like, yeah, this also have this. We know other, do you, which one? Spec of A and spec of B. When you want to intersect two affine schemes, for instance. Really? So you also have this has section, but have the properties that tell me if it has this property. What I'm going to write now, I will write some property, and if you can. Really? Really? I will write now the property, and maybe you can tell us if it's really this property. Maybe you need to check also. It's not that obvious. Maybe, yeah. Let me write the properties. Yeah, exactly. So the for pullbacks, not for product, right? You mean? I mean, like this map. It's for like when you have a pullback diagram, like you have this x, y, z. Yeah, for pullbacks. Okay. Just to get the intersection of x and y inside z. But let's say all of them are affine. So x is like some step A, y is like some step B, z is like some step C. The resulting space is spec of A tensor B. Okay. Yeah. And okay, the first what we say is section is is section for, as we said, like for this natural one, y. The other property is, okay, naturality. It's not natural. This, yeah, it's not natural. Like they, for example, they ask it to be natural, the one that, but it's not natural. But it's have something like we need here. Really, it's important that if we have such a diagram, yeah. So then, if let's say we have such a diagram, then when we apply m of fg, we mean f of g is that the one that coming from this. Okay, if we apply this and then we apply t of beta y beta, then we apply the maps, then it's the same as, so it's natural when we have such a map. Okay, in fact, I will say something. Okay, let me write maybe this. Like we here, we apply the maps, the maps, and then we apply m. So it's natural in this case. Actually, in fact, it's natural when this is injective. It's more, but we want to write it in, actually the advice of your students ready told me this is, but it's really like if we want to write the properties that the more general property, it's natural when this one it's injective. It's natural. But this, in order to write it in much more natural way, let's say, yeah. This you can write it like this, yeah. And the other property that this is, by the way, known property for simplicial distribution. People use this for compositors. There is this paper of compositors. So this is a property that's saying that if you have such a diagram, if we have such a diagram, and we taking like two, like P and Q in the T, like here TE, TZ, with Tx, like we taking this, and we try to glue. First of all, we applying like T pi on Q, like let's say which is pi, like this. We applying, this is a Q. We applying this one. First of all, T pi on Q. If we apply this, and then we try to glue with P, we glue with P, like P is here, distribution on here. Q is here, so we gluing this, so we get something in here, right? We glue with this. If we do this, and then we, if we glue with this, and then we glue all of this, like this is here with Q, is the same as gluing P and Q. Okay, this is like, it's called like back and forth, going back and forth. Yeah, like going like this. If we want to glue this, but we can, it's the same as to go like this and to glue this to give me something here, and then to glue this to distribution or anything, like it's depends what we are thinking. Do you think that this property is also, you think about this? It's you need to check, of course, like it's not like easy to see. Yeah, but it will be nice, like if it's, yeah, if it's really okay. Now for unit, now the naturality of unit and the naturality of maybe one can think about this, the naturality of unit and the naturality of the multiplication. So the naturality of unit, it's hold. Like what we mean, like if we have this, and we taking the delta x, delta y, like to going to here, and then we glue. So it's the same to taking like delta of this. Okay, so this is hold. But for the multiplication, it's not really hold, but it's hold in some case that we need. Okay, it's hold in one case that we need. Now for this, for multiplication, like how I can write it, it's like, okay, like what we want here, like we want, like if we have T, if we have, like we started from this, let's say. We have such a diagram XY, and we started from this. So one can do at the beginning the M, like normal M for T, like for the all, and then to get this, right? Like applying M to get this. And then one can do T of M on this, right? T of M on this in order to get this T twice of, right? And then mu of this, right? But there is another way to do this, like in the other direction, like what is this? To apply mu twice, mu of x, mu, to get this. And then to apply the m. Yeah, so this diagram not commuting, no, it's not. Like, but in, yeah, we know, like in when they doing this for the mono, for this, for mono, they asking this to be commute. But this is not, but it's commute when we have, like when we starting here with some P, but here the other one, it will be delta of something, yeah. Like, yeah, you know, We need this, by the way, for our concept exactly to prove. I already erased it, but in order to prove that this is functor, exactly we need this. Like, yeah, to be commute in this case, like in some when, like not all commute, but this, like if we, I think, yeah, there is a map like from here, right? That this is the identity, and something here from Y. There is a map, like so. This commute when we compose with this map. Before it's not commuting. This is the properties that we need. And the distribution monad applying this, also maybe there is other question, but for us is important the distribution monad one. Okay, so we have this functor, two categories. This functor, the bundle T. And now in order to get scenarios, we will apply the Grothendieck construction on this functor. And this category give us the category that we want. But now we're doing this in general for C. We want to do this when D is a distribution monad and C is the simplicial set. Okay? Yeah. Is stochastic version? Yeah, lower T. Yeah, right. Yeah. It's depend on T. Yeah, exactly. When we have the identity, we will call it like this, right? But it's depend on T, right? So this is a scenario, but we want this actually. So in fact, but okay, we need simplicial, like C to be simplicial. So we need to take, like, let's say, okay, for D, if we take D and to be the monad and set, it's okay, it's work. But the thing that this M, we don't have this M in simplicial. Like this M, it's not working in simplicial because it's not a simplicial map. What I mean, like if we take it, because there is no naturality. Like for the distribution monad, if we take this distribution monad, we say that we have D of X, D, Y to T, this map, the glowing map. We called it the glowing map, but it's not natural. Like one of the property at the beginning was that it's not always natural. It's natural when this is when the map of this is injected. Like if we're taking now another map to, so it's not commuting. Like by the way, the degeneracy map commuting with the degeneracy map, but it's not commuting with the faces map because the degeneracy map is injective. So it's not good. But anyway, like we have this map, like we have M. If we're taking here simplicial sets, if we are working in simplicial set, so we have this map between this, but it's not here. No, it's not here. But still, we have this map. Okay. So if you remember when I defined it was something like this when we defined how pi is acting, or this pi, we call this pi. If you remember how it's acting on alpha, it was something like this, like alpha delta y, and then we apply M, right? Yeah, and then we apply M. So this, by the way, if we're taking simplicial map, this will be really simplicial. This is natural. This is natural. Like M by itself, it's not natural, but this is natural. So this is enough. So this is the reason that we can actually doing this also for simplicial sets. Even though, like maybe one can think, I'll say, okay, but your M, you using this M, but if we taking this from simplicial set to simplicial sets, okay, there is, you can do the distribution monad acting on also, like it's also a monad in simplicial set, but it don't have this M because M going outside. But we don't need M to be inside the category. We need only this to be inside the category after applying this, yeah. Which is so we can do this, and we can get the simplicial version of this, like if we have this property that this inside the naturality of such something like this. So actually this is what we want to talk about. Like we want to talk the C to be the simplicial sets and D, and this we called it simplicial scenario, the simplicial scenario over D, okay? Simplicial scenario over D. And how morphism look like in this category? So morphism, like object, of course, as we started, but morphisms F to G so morphism is a map from, like one can check is exactly the Grothendieck construction telling us this and telling us even how it's a composition. There is no time to explain, but so the it will be something from here to D of F, D of E, and we have okay delta sorry E of Y, Y delta Y. So this is how looking morphism in this category. Okay. Okay, composition. It can be exercise how to do composition. Okay, so we have this, but we want also to define the simplicial distribution functor. But again, sorry, like it's this one. We need the identity here to get our category from the beginning. We wanted this category, but right. We wanted this category, but this is inside, like by using, there is a functor, like from this category that inducing by the delta to this category. One can imagine how it's look like, simplicial to simplicial scenario D. Then, but then the morphism without this D, like what we explained before, like then this will be the identity, okay? This is the category that we're interested in, but it's included in much more bigger category. And we can actually defining here the simplicial distribution functor inside this, the simplicial distribution to convex. So how we can do this? Okay. So in fact, we can do this in one way to do this is to taking this delta, like from this, yeah, there is a functor, to taking this functor, the simplicial scenario, the representative functor from this scenario, delta 0, delta 0. This is also scenario. This, but it's not obvious that it's so convex. Maybe we can explain this, but this is a functor, right? Like because this is a category. Like for every category, we can like always doing this representative. If one think about this, if we think a little bit about this, this is exactly giving us, because what is the map from? Like if we're taking any F, where it's going, this F, it's going to all the maps from this to F. So what is the map from this to F? As I explained there. So it's a pi here, and let's say this is F. So we have delta X, T, X, E, T, F, right? But we need from the pullback of this. So what is the pullback of this? This is the identity, right? Because this is the identity also, yeah. So it's exactly what we explained before, like simplicial distribution, right? It's only this that side. So it's, as we explained at the beginning, you remember, like simplicial distribution is a map from X to this, that making this diagram commute. So we can take this. Actually, in order, now maybe it's harder to prove that this is lying convex, but it will be easier, like we can doing something like this here. We can taking, in fact, we have a map. We define a map from simplicial set, a functor, sorry, this the bundle one from here to categories, right? But in fact, like we can get from every x, for every x, we can get a functor here. Not only like a functor that end in convex. Okay, how we can get this? Like we can say, okay, this functor will be with simplicial bundle here, the x going to convex. How it's defined, this functor. This functor actually sending everything to simplicial bundle, because this is a functor, right? Simplicial bundle of x for the identity xx. Yeah, like everything here, I'm sending fx, let's say, I'm sending to this from the identity to x. So what it looks like I'm sending it to this actually set. So what is to some sets? What inside this set? Actually, inside this set, it's a map like this. T E. Yeah. So it's a simplicial distribution as we explained at the beginning. Yeah. So we can do this, and in fact, like this is a functor, but in functor, not like here, it's the category, it's not exactly the slice category, but it's the field slice category, because like if we have such two functors like this, like if we have such a map like this pi, then it's not exactly give me, like maybe let's call it's I don't know, like maybe I will call it fx. Okay, so we have this fx to convex, and we have fy, and we have a map from f, let's say from y to x, so it's contravariant. We already know this is a map pi star from simplicial bundle d x to simplicial bundle dy. But this is filled, like it's not commute, but this is filled. So this is not exactly the slice category here, but it's when the morphism are maps like this that filled by natural. Actually, the naturality comes because like this pi actually send the identity. This pi, it's sending the identity of y to the identity of x. Okay, this or a simplicial bundle, like sending this to this. So one can think about it, and here we can fill it by using pi. So in fact, we have like this. You see, like we have this functor from simplicial, not to categories, to functors here. When they down, when we down to categories, like there is a projection here, it's give us exactly what we had before. Okay, but there is generalization of the Grothendieck construction to this. Like all of this will give us a functor. Okay, like because if we're doing this to categories, this gives us a category. Now if we're doing, there is generalization of this, that gives us a functor. Okay, if we're doing and this exactly will be this functor, the simplicial distribution functor. But this will be easier to prove that this lie on convex sets. This will be easier because all of this lie on convex sets is easy to prove. Okay, so okay, this is a general construction. But let maybe us to do some application now. Okay, so this can help to do some application. I don't know how much time I still have, right? So yeah, I still have time. So let me do application of this. So what we have so far, we define this category, the simplicial scenario. Actually, we define something more like this inside the stochastic one, which you have said it's inside, but we need this for now. Okay, we define this and the functor of simplicial distribution to convex. Okay, this we have morphisms here. So now this category, have a monoidal structure. It's coming from the monoidal structure of simplicial sets, from the product, sorry, for simplicial sets. So if we have like F and G, so then there is a new one like this. Okay, so this actually, in fact, it will be here like a monoidal. It's in fact a monoidal, symmetric monoidal structure. Okay, this make it symmetric monoidal category, make it. And also, like we have like this coming from product, and we know that in simplicial sets, like in simplicial sets, we have this product, but this product, it's actually like have like we have this in simplicial sets. We know this property. Let's say that there is natural isomorphism to simplicial sets of X map, right? So we want actually to generalize this, because we have now for simplicial scenario, we have tensor product here for F J H, and here to have this, okay, to have this map, simplicial scenario, sorry. F map G H. We want to do this. We hope there is something like this. Why we think like this? Because actually this category is generalized the category of simplicial sets, right? Like we can have this, like if we have here only a point like delta 0, then we are in simplicial, like simplicial sets is included, like every simplicial set we can think about this, and also a map, like it will be the same. Yeah, so if we have like this delta 0, sorry, delta 0, so we want to define this, in fact. So how it's defined here, like let's remember how it's defined here. So it's defined, let me maybe write here, okay, I have map of X, Y, let's say, how it's defined there. So in n degree, it's exactly, it's simplicial set map from X delta n to Y, right? This is in the degree n, right? It's like this. But we can think about this, okay, like we have X, this X, we can think about this as a bundle, which here delta 0, right? And here we have Y, it's also a bundle, which also with delta 0. But actually I need now to give me this map will, like in general, if we have, instead of simplicial sets, we want simplicial scenario, okay? Simplicial scenario. But instead of this, I need to have some maps. So here, instead of this, I need here a product. Like instead of product, I need here tensor product. So it will give me, if this is delta 0, so it's delta n x, or x delta n, that's the same. The products will give me the pullback, and then it will be a map from here to here. But this one, how to do this map from here to here? So I need also to give this one something else, because it's y, it's to delta n, it's the y, the original y, it's to delta 0, the original y. So in fact, it's this one. To get this, like we get the pullback of this by going this. So this will give me the whole y in this case, because here this is surjective. Yeah, so this is give me the whole y. Now, okay, we did it. Now we did it when delta 0 is the base. But if we take the base to be general, to be what? The pullback of this. Yeah, also the pullback. Yeah, yeah. So I get this map. how we got this map. I want to explain how we got this map. Yeah, but here actually, in fact, okay, just a minute. Y cross delta n, we need not y, just a minute, yeah, y cross delta n, yeah, y cross delta n. But because it's like easy, like it's going exactly on y, so you are right, y cross delta n. But in fact, like this map, it's just what not the pullback. Just y, you think? It's not y. Just a minute. Just a minute.
Because I think that's how you define the maps. You didn't say.
Yeah. No, if we taking this, why I thought it's y. I was thinking about this before. So why I think y, and maybe I just a minute. If we taking this delta n to delta 0 and y, so we need something from here and something from here. No, it's y delta n, right? It's right what he is saying. Y delta n, yeah. He's right what he's saying. But why I want here to be y. So I thought about this, that we can do this in order to be y. Just a minute. So we taking here, we want the same, because I need the map like this, to be a map like this, in order to show that really it's generalizing this one. So let me think a little bit how it could be y. It should be the same y. If we taking delta x, so it will be only a map.
You don't need to pull back into target, right? So you just want to motivate the mapping.
Well, actually, because here you need only, like if you're doing this, you will take only a map if this was delta n. So it's this map. It's only a map from x to y, right? Because it's nothing, right? Because it should be the same down to delta n, or it's not. If we have that, yeah. If they going to the same base to delta n, my question is that mean that we have here a map from x to y? No.
Yeah.
Only for x to y? No.
The target, the delta n doesn't make a difference to the target. Having a delta n there doesn't make a difference.
Having the very same, but I wanted here to get the map from this, like it will be changed from y to y. No, but just a minute, like, but here is a change of this. Now I see it. Yeah, you are right here. But here, if we think, no, this map actually it's a map from this to y, right? Yeah, this one. Yeah. This is what I wanted. Yeah, but yeah, exactly. And so it's right. Yeah, I don't have to make it right. It's right. Yeah. So this actually exactly a map from here to here. So why I want to do this actually, because I want to explain how we can generalize this to this. So now we think in this, but now we change. Like here, I took all the bases to be delta 0, because I want to be here. But if we are here, the bases don't have to be delta 0, but we can do the same definition. Like in order to do, we can do the same definition, like now the mapping n, mapping x, y, n, it should be some mapping scenario from, now instead of this, like ex, now we will take here e, x, and here delta n, and here the pullback of this, and here, but here not really, we're not taking exactly y, we take again the pullback of this, like as we did before, like we take the pullback like delta m of something here, y, so we should choose some y here, we should choose some y here in order to do this g, and we take this, so let's call this gy, okay? So we're taking actually from scenario from f to gy, but we choose some gy, so we take all the union over gy, yeah. In fact, this is a definition of Cihan, but I try to explain how he said. You thought like this? No, maybe you thought another way. I don't. This is your definition, by the way. It's not. Yeah, I try to make motivation for this. Yeah. So simplicial scenario. So really, this is exactly when we think about fg here. Sorry. But if we taking this like xy, because it's including the simplicial sets, including this will be the same, this one. And here one can think about how the there is, because I need not only this is above, but it's down to y. This down to y, like this is the n space, but this down to yn, and there is really simplicial map. And one can think really, it's not that hard to think now about the how it's look like the faces and degeneracy map. Actually, it's coming from the simplicial structure of y. One can see because we're taking here y. But the thing that it's not true. This is not true. It's not really true. But it's have some good properties. This is, even if it's not true, there is one direction. This direction, it's right. Like there is inclusion from this to this. And the good thing that it have this property, like when we're taking the unit of this monoidal structure, it's true. Like if we're taking here delta 0, it will give me here this one. Okay, it's true when we have this unit, and we now doing some application of this in maybe in 5 minutes. Maybe I can do this. Okay, let's do some application of this. You know what I'm doing now, it's something that generalized, something that done also in some Bill Buxton's this paper of Rui and Martin. Okay, so what we can do here actually, we can think about this thing, like we have every map of, if we have a map from a scenario, simplicial scenario fj, so it will, this map induce a map from simplicial distribution, because there is a functor of simplicial distribution, from simplicial distribution f to simplicial distribution g. And we already show that this one is convex, right? It's in convex. Yeah, right. But one can ask, okay, what if we have something like this convex? Is that coming from here? This is one question. Like if we start from some convex map from this is a convex set, and this is convex set, but not every map from here to here that sending simplicial distribution on f to simplicial distribution g is convex. So is every convex map coming from here? Of course not, because actually we can, like this map, there is a natural map that coming from the functor, like there is a natural map from here to here, to convex of simplicial distribution f, simplicial distribution g. There is a convex map like this, but because actually this by itself is a convex set, this is a convex set, so we can actually generalize this to all the distribution on this, right? Like every distribution on this also give us something. Yeah, there is like more, like every convex combination like of this give us also convex map from here. So is that all the maps, or which maps? Like here is the question, like which convex maps coming from here? Okay, yeah, which convex maps from simplicial distribution of f to simplicial distribution of g induced by induced by convex combination of scenario morphism of the scenarios. Yeah, this is by let's say, okay, by morphism between the scenario, like convex combination of the scenarios. It's important because actually, like this is called like simulation, like every, like something give us simulation from this to this, how we can simulate some simplicial distribution by other. So it's important to know which convex coming from here, and it's related to this mapping space, because in fact how it's related now to this mapping space, because in fact, there is a map also from mapping. Let me maybe write here. One can prove that if we have mapping from Fj, just a minute, like, sorry, simplicial distribution mapping of J. Simplicial distribution on this scenario, yeah. This actually acting also in this, like it's give me convex map. Simplicial distribution F, simplicial distribution, just give me one. Okay, there is like really natural construction here from here to here. Let's call it, I don't know, Fg. There is something like this, and in fact, if we're taking now this scenario, we can look at here at this adjection. What I saying here, this one, we say that this one is equal to this. But what is this one? This one is exactly G, scenarios at GH. And this one is equal to this, like scenarios from the identity to this one. But if one thinks what is scenario from this to this is exactly section of this, simplicial section of this one. Yeah. Because like this is, we can, like this is a map, so section of this map. Okay, this is exactly section of this map. So, but now we have actually, in fact, we have a map from D of section, from D of section of mapping Fg, this map that tell me which one here is contextual and which one is not. Theta of mapping Fg, like, because maybe I didn't explain, we explained it in previous talks. Like, we're interested in simplicial distributions, that okay, which one is contextual, which one it's not, which one is coming from joint distribution, which one it's not. Okay, so we have this. And in fact, like this, as we explained before, there is a natural map from this to the other one, the scenarios of from F to G. Okay, and this exactly this map. So this, the diagram here commute. In fact, the diagram here commute, like this map is exactly this. So now we can answer the question that we can say this characterization using contextuality on the mapping scenarios, like this is called the mapping scenario. So we can say here the answer about this answer. We can say exactly the ones that induced by simplicial distribution on mapping, but not exactly any one, because it's exactly the ones that coming from here, right? So it's the non-contextual ones. None. This map. This. No, this map, it's not it's not really maybe because you no, it's not really surjective maybe. No, it's not surjective. It's not should be surjective, because but it's that you can have another convex, but we ask which is coming from here, from like it's coming from simulation, like what it's called simulation, like it's something that a morphism between scenarios. Like we have this morphism between scenarios, like this with pullback, and this induced a convex map here, right? Or any convex combination. But not every convex map here is coming from this. Which one coming from this? So if you have something here that coming from this, from something here, so of course it's coming from something here. But what is something here? Like from non-contextual simplicial distribution of map. Yeah. Yeah. So here is the question: what it's considered? Like we have simulation, but we have maybe another degree of because every simulation coming from something here. This is the definition of simulation. It's the map that coming from here. But we see that there is another like kind of really maybe this should be studied. What is the things that coming from here? Yeah. Yeah, that is I think. Thank you.
Okay, thank you. Okay, so are there any questions for Aziz? Okay, maybe here. Any questions?
No, if I want to find this, it's here maybe. No.
Any questions on
Yeah,
Zoom?
I found it.
Can you hear me? Okay, no questions. So let's end here. Okay, thanks, Aziz.
Thank you. Thank you very much.